So in this class I will discuss how to solve the hyperbolic equation. So as we know, the wave equation is an example of hyperbolic PD. So let us consider the wave equation of the form utt equal to a square uxx, and let us call it equation 1. Here u, the derivative of u with respect to time variable t 2 times, and the derivative of u with respect to x, the space variable, 2 times. So in order to find the numerical solution of this equation 1, we should have two boundary conditions, means two conditions related to x. Those are called boundary condition, and u of 0 t equal to 0 one boundary condition, u of lt equal to 0 another boundary condition. And since it involves two derivative with respect to time variable t, so we need two initial condition. So one initial condition will be initial displacement, that is equal to u of x0 equal to f of x, and the other condition will be initial velocity, so ut of x0 equal to 0. So let us try to solve this hyperbolic PD. Now here we will consider the x step size as h, delta x equal to h, and t step size as delta t equal to k. As we know, the second order derivative of u with respect to x can be written as ui plus 1j minus 2uij plus ui minus 1j by h square, denoted equation 2, and utt equal to uij plus 1 minus 2uij plus uij minus 1 by k square, and denoted as equation 3. If we use equation 2 and 3 in equation 1, the equation we get is uij plus 1 minus 2uij plus uij plus 1 divided by k square is equal to a square by h square into ui plus 1j minus 2uij plus ui minus 1j. Now this again can be written as a square by h square into ui plus 1j minus 2uij plus ui minus 1j minus 1 by k square uij plus 1 minus 2uij plus uij minus 1 is equal to 0. If we consider lambda equal to k by h, we can rewrite the above equation as lambda square a square into ui plus 1j minus 2uij plus ui minus 1j minus uij plus 1 minus 2uij plus uij minus 1 equal to 0. This k square I took to this side, and if we rewrite once again this one by taking the similar coefficients, I will get uij plus 1 from here, and uij, here uij 2 is common, 1 minus lambda square a square uij plus lambda square a square ui plus 1j plus ui minus 1j minus this term uij minus 1. So this you denote it as equation 4. So equation 4 is called explicit scheme or explicit formula to solve the hyperbolic PD. Now here I want to give you some note on this formula. This is the explicit formula. Now this formula is stable, or the solution which can be obtained by using this formula is stable if we consider lambda equal to 1 by a. If we consider lambda equal to 1 by a, means this term will be 0 and this one will be 1 by a square will get cancelled 1. So the value we will get is uij plus 1 is equal to ui plus 1j plus ui minus 1j minus uij minus 1. So for lambda equal to 1 by a, we can have k equal to h by a. So if you know h, you can able to calculate k. If you know k, you can able to calculate h. So that is why in case of explicit formula we consider lambda equal to 1 by a, and we get the relation 5. So this is the formula we will use to find the value of u at the grid point I j plus 1. So we can represent this one in the schematic diagram as if this is uij, this is ui plus 1j, this is ui minus 1j, and this is u. Just I am reversing the position. This should be down, but I want to find this one, that's why I am writing it. So uij plus 1, uij minus 1. Then in order to find the value of u at the grid point ij plus 1, we should know these three values: one left to uij, one right to uij, and one will be above to uij, and so above down to uij, and so we will get this plus this minus this equal to this. So this is the schematic diagram for this scheme. Another note I want to give, so here, so boundary conditions are given and initial conditions are given. So how can we use the boundary and initial conditions? So first boundary condition is u of 0 comma t equal to 0. U of 0 comma t is equal to 0 means x equal to 0 here. So if I take the line x equal to 0, whatever t it may be, the value of u will be 0, and I can denote it as u0j, because x is 0, t is j, so u0j equal to 0, and that means along the line x equal to 0, value of u will be 0, all value of u will be 0 irrespective of j. Similarly, if I go to the second boundary condition, u of lt equal to 0, where L is the length of the string, and so I can have u of nj, because L is the length, so I can write n, so unj is t, so I can write unj equal to 0, and this implies along the line x equal to L. X equal to L is the line parallel to y axis. X equal to 0 is the line which is y axis. So along the line x equal to L, all values of u are 0. Again, note 3 is how to use the initial condition. So first column here will be 0 for x equal to 0, and the last column will be 0 for x equal to L. Now two initial conditions are given, so how can we use them? First initial condition is u of x0 equal to f of x. So x is I and t is 0, so ui0 equal to, here f of x is nothing but f of ih. In case of h equal to 1, we can write f of I. For I equal to 0, 1, 2, 3, 4, and so on. So this gives the value of u, one is u for various value of I. And note 4 is for the second initial condition. Second initial condition is nothing but ut of x0 equal to 0. Ut of x0 means derivative of u. It is not like simple u. So we have to write this one in the partial quotient, and we have to use the thing. So ut of x0 equal to 0 means, you know, ut is uij plus 1 minus uij minus 1 by 2k equal to 0. At j equal to 0, and using the central difference scheme, we will get uij plus 1 minus uij minus 1 by 2k is equal to ut x0. And so this uij is 0. So if I put j equal to 0, ui 1 minus ui minus 1 equal to 0, and so I will get these two relations. So if I use the relation 7 in the equation 5 for j equal to 0, and if I simplify, I will get ut of x0 equal to ui1 is equal to ui minus 1 0 plus ui plus 1 0 divided by 2. So here, depending upon the I, we can able to find the initial condition. So in place of ut of x0, we will write ui1 ui minus 1 0 plus ui plus 1 0 divided by 2.